Okay, so let's continue on with our discussion of acids and bases. And the next topic we're going to cover is amphiprotic. Protic means a proton or a hydrogen ion, and amphi is just like amphibian. It means it has two natures. So it can do two different things with a hydrogen ion, is what that means. And so it can serve either as an acid or a base. It can either accept a hydrogen ion, and that means it would act as a base, or it can donate a hydrogen ion and then will act as an acid. And so water is one example of this, where it can act as either an acid or a base. And try and write those two equations for yourself on these slides. If you have trouble with it, let me know and I can do another video and just show you real quick how to do that. So one would be where water acts as a base, and one would be where water acts as an acid. So this is called the autoionization of water. And so I want you to try and do that here. And again, I will answer that later if you need me to. And I also want you to do it as a base where where we have a base present and water acts as an acid. So go ahead and do that here as well. So in pure water, water will act as both an acid and a base, and we will have some of each ion present. Go ahead and try and write that equation here. Of course, if you have difficulty, post it to the discussion board on Plus Portals, and I will answer it there. And at 25 degrees Celsius, or room temperature, the Kw for water is 1 times 10 to the negative 14th. So that means that the concentration of hydrogen ions and hydroxide ions would be the same, and each would be equal to the square root of that number, which would be 1 times 10 to the negative 7th, and that's where we get a pH of 7. We'll get to all that later. So, since Kw equals the concentration of hydronium ions and hydroxide ions in solution, then we can take the pOH, and hopefully you've already read about that. And to do a pH, it means, and you'll have to write this down, it's not on the slide. So again, this is something where you're taking notes. pH is equal to the negative log of the hydrogen ion concentration. And so for water, it would be the negative log of 1.0 times 10 to the negative 7th. And if you do that in your calculator correctly, you should get 7. So when the concentration, and if we do the same thing for pOH, we would get the negative log of the hydroxide ion concentration, which should also be 1 times 10 to the negative 7th. We take the negative log of that, then we get a pOH of 7. So it would be a neutral solution. So when we have pure water, it dissociates, producing 1 hydronium ion and 1 hydroxide ion for each 2 molecules of water that dissociate. Since these are equal to each other, it means that it's neither acidic nor basic, that the amount of hydrogen ions and hydroxide ions are equal to each other, and so it would be neutral. When we add an acid or a base to water, we would get a situation where they are not equal. However, the concentration of hydrogen ions times the concentration of hydroxide ions always has to equal 1 times 10 to the negative 7th. It can never, 1 times 10 to the negative 14th, sorry. It can never be any other number. So, as the hydronium ion concentration increases, hydroxide ion decreases. So they're inversely related to each other. And if the hydronium ions is greater than the hydroxide ion concentrations, then it would be acidic. And if the hydroxide ion concentration, and that's what those brackets mean, remember that, then it will be basic if we have more hydroxide in solution than hydronium. So the acidity and basicity of a solution can be expressed in terms of its hydronium ion concentration or its hydroxide ion concentrations. And these can be very large number, or very small negative exponents. So it can go from basically 0.1 to 1 times 10 to the negative 14th. That's a lot of orders of magnitude. And that's why we use the negative log of the hydrogen ion concentrations to compress that scale and make it easier to deal with. So, what does the P mean in POH, pH, pKa, pKb? And pH plus POH equals 14. P in chemistry just means negative log of the concentration or the number provided. So for H and OH, it would be concentration. For Ka and Kb, it would be their the Ka, or the rate constant, not rate constant, the equilibrium constant for that acid or that base. And we only use Ka and Kb with weak acids and weak bases. You will not find Ka or Kb for strong acids or strong bases. And I think we've already mentioned those. If not, we will. So, if they're equal, we have a neutral solution, and they're both 1.0 times 10 to the negative 7th, and that is at 25 Celsius. If you change the temperature, you do change that Ka value. You should be able to tell me if it is acidic or basic by looking at what those numbers are. So if it were 1 times 10 to the negative 6th, then it would be acidic. If it was 1 times 10 to the negative 9th, it would be basic. So you should get familiar with doing those calculations. So when it's acidic, hydronium ions is greater in concentration than a hydroxide. pH will be less than 7. If it's neutral, pH will be 7, and the two concentrations are equal to each other. And if it's basic, the hydroxide will be greater than hydronium, and it will be a pH greater than 7. And this is a table in your book. So, here's a relative scale of various things that we find in real life, so to speak. And gastric juice is on there and has a pH somewhere between 1 and 2. This is why it's very bad to be bulimic, because that gastric juice is pretty acidic and it'll actually eat away the enamel of your teeth. Most things that we eat or drink are acids. There are a few exceptions to that. And then most things that we clean with are pHs above 7, which makes them good cleaners, like ammonia, etc. So, you should know these relative terms. I'm not asking you to know any particular ones, but if I give you something like lime juice, you should realize that's got acetic acid in it, or citric acid in it, and therefore it would have a pH of less than 7. So, pHs of strong acids and solutions. Oh, here it is. In Chapter 7, we were told that there's 7 strong acids. You need to remember these. These completely dissociate in water, and they will have a pH that is well below 7, depending on their concentration. I want you to draw in your notes a particulate or particle view of what it means when I say that it completely disassociates from water. I want you to have 7 molecules of HCl disassociated, and I need you to include 7 water molecules. So make sure that drawing is in your notes for submission to Plus Portals in eLocker. Guess what? I'm also going to ask you to do the same thing with our strong bases. Draw a particular view, what it means with 7 formula units of calcium hydroxide. You must use calcium hydroxide. I would include water molecules, but they're not necessarily essential. So I'm going to stop here for today. Please let me know if you have any questions or comments, and that would go in Plus Portals under discussion. Thank you.